Okay, this is lesson 5.4 on multiple angle identities. So when it says multiple angle, it means like, in this first case, double angle identity, when theta is actually itself doubled. So we have, for example here, sine 2 theta. That's not a squared. That's when the angle itself is doubled. So like going from, if theta is 60 degrees to doubling it, which is 120 degrees. And what would that look like? And we also have one for cosine 2 theta. And what that means is we actually have 3 different ways to write this identity, depending on what we have in the problem. So you don't have to have the whole thing, but one of those 3, any of those, would set up an identity with cosine 2 theta. And then tan 2 theta is equal to 2 tan theta over 1 minus tan squared theta. In example 1, we're going to apply that double angle identity, and in this case it's for sine 2 theta. So the identity that we're going to use is sine 2 theta is equal to 2 sine theta cosine theta. And so we want to be able to prove that identity. So what I'm going to do is I'm actually going to start with the left-hand side, and you really can start in either side and go either direction. But I'm going to start with sine 2 theta, and I'm going to write 2 theta as a sum, so that I have sine theta is, instead of saying sine 2 theta, I'm going to have theta plus theta, because theta plus theta is 2 theta. And now I have the sum of a sine identity. And so for the sum of a sine, I have sine u cosine u plus cosine, back up there, cosine v plus cosine u sine v. Well, u and v both are theta in this case, so I've got sine theta cosine theta plus cosine theta sine theta. Now you can see we almost have exactly the same thing. The order's just different, and multiplication is commutative, so actually we can switch sine and cosine around any way we want to help us kind of match more of our identity that we're trying to prove. I am going to leave the first one, sine theta cosine theta, but the second one I'm just going to switch the sine and cosine so that I have another sine theta cosine theta. And now I have 2 of those, so that's going to equal 2 sine theta cosine theta, which was what I was trying to get. There's my identity. Okay, so a few more identities here. We have a power reducing identity. So power reducing means going from a higher power, like in this case the second power, to something that's written in the first power, which is what we did. You notice that on the left-hand side, those are all to the second power, but on the right-hand side, there are no exponents of 2. Nothing greater than 1. Okay, for example 2, it says, prove the identity cosine 4 theta minus sine 4 theta is equal to cosine 2 theta. So you can see that in the power reducing identities that we only have squareds and not fourths, but we can kind of take care of that because something to the second power is to the fourth power. So that's like taking x squared and squaring it. That's going to give me x to the fourth. So I'm going to take cosine of 4 theta, or theta to the 4th, and that can be written as cosine squared theta squared, and sine of 4 theta is sine squared squared. So those are the different ways of writing to the 4th power. I'm going to take those ideas along with the power reducing identities and work this problem out. So cosine of 4, or cosine theta to the 4th, is cosine squared theta squared, and then sine to the 4th is sine squared squared. So I'm going to replace what I have for cosine squared and sine squared from the power reducing identities. So I have cosine squared is 1 plus cosine 2 theta over 2. And then minus, what we have for sine squared is 1 minus cosine 2 theta over 2. I'm going to square that. So I have to take each of these and square it. So we square the numerator and then we square the denominator. So if I have 1 plus cosine 2 theta times 1 plus cosine 2 theta, that's going to give me 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta over 4. And then on the left side, and then I think the in parentheses are important here, we're going to square that, so that 1 minus cosine 2 theta times itself would be 1 minus 2 cosine 2 theta plus cosine squared 2 theta. All over 4. So they're both over 4. We can really just combine the numerators. Just be very careful that you distribute this minus sign. So that gives me 1 plus 2 cosine squared theta plus cosine, or 2 cosine 2 theta, cosine squared of 2 theta, minus 1 plus 2 cosine 2 theta minus cosine squared 2 theta. All over 4. So I'm going to simplify the numerator. My 1's are going to cancel. And then I've got, I can see that my cosine squared 2 theta are going to cancel. And I'm left in the numerator with 2 cosine 2 theta plus 2 cosine 2 theta, which is 4 cosine 2 theta. And then over 4, which is cosine 2 theta, which is exactly what I wanted. For example 4, it says rewrite cosine theta to the 4th in terms of trig functions with no power greater than 1. So you can't have second power, third power, any of those. Everything has to be to the first power. So I'm going to start with that concept again, that cosine, we don't have cosine to the 4th identity, but I do have cosine squared. So cosine to the 4th of theta is equal to cosine squared theta squared. And so I can replace cosine squared with 1 plus cosine 2 theta over 2. And then I'm going to square that. So that the numerator is 1 plus 2 cosine 2 theta plus cosine squared 2 theta over 4. Now I've got another squared term because I have cosine 2 theta. So I'm going to take that concept of the power reducing identity, that cosine 2 theta. So 2 theta, that whole thing together, is really my angle, and we can count that just like we do theta. So for the identity, it would be 1 plus cosine of 2 times theta, 2 times 2 theta in this case, which would give me 4 theta over 2. And then I'm going to put that back up for this. Okay, and what I can do, these are all over 4 here. What I could do is basically go through, and those are divided by 4, which is the same as multiplying by 1/4. In those parentheses, plus 1 plus cosine of 4 theta over 2. So that when I multiply everything by 1/4, I get 1/4 plus 1/2 cosine 2 theta plus 1 plus cosine 4 theta over 8. So that gives me 1/4 plus 1/2 cosine 2 theta plus 1/8 plus 1/8 cosine 4 theta. So I can combine the 1/4 and the 1/8, which would give me 3/8. Of cosine 2 theta plus 1/8 cosine 4 theta. That one was a little bit tougher one, so we've got a lot of squareds going on there. We have a few more identities here. This time we have the half angle identity, and that's where we take an angle and we divide it by 2 in half. So if theta were 60, if we're doing a half angle and dividing by 2, then instead of saying sine of 60, we do sine of 30. Okay, example 4, using the double angle identity. Solve algebraically in the interval 0 to 2 pi. So basically we've got to figure out what theta is going to be to make this identity true. So that means using the unit circle to help us find x. So I have sine of 2 theta equals cosine theta. And I want to replace that sine 2 theta with our double angle theorem, which is 2 sine theta cosine theta. And that equals cosine theta. And then I'm going to bring the cosine over to the left side by subtracting it. And that gives me 2 sine theta cosine theta minus cosine theta equals 0. And I get extra sneaky here and factor out a cosine from both of those. If I factor out the cosine, I have 2 sine theta minus 1 equals 0. And here's where I might put in some variables. Remember that cosine is x and sine is y. And we want them to equal 0. So what we're going to do is we're going to set each of those factors equal to 0. We've got x equals 0, and we've got 2y minus 1 equals 0, which give me y equals 1/2. So I want to know what happens when I have an x coordinate of 0 or when I have a y coordinate of 1/2, and that's where the unit circle is going to come in. So let's say x is equal to 0. Well, where does x equal 0? X equals 0 at pi over 2. And x equals 0 at 3 pi over 2. And then the other option is where y is equal to 1/2. Well, it's at 1/2 at 30 degrees, which is pi over 6. And then also at 5 pi over 6. So those are our really 4 solutions there. Pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. And there aren't any excluded values because we don't have any fractions for this problem. Last problem we're going to do, it says using half angle identities. So we're going to apply our half angle identities to this problem. And actually I'm going to do this as a two-sided proof, I think. So I have sine squared theta, and I have 2 sine squared theta over 2. Let's see, sine squared is 1 minus cosine 2 theta over 2. Minus cosine of 2 theta over 2. And then we've got our half angle there. So we've really got a couple of things going on because we've got a square and a half angle. I'm going to rewrite this. Instead of saying sine squared of theta over 2, I'm going to do sine of theta over 2. And then square that so that I can replace sine theta over 2. And I'm going to use my half angle identity. My half angle identity says that sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta over 2. So on the left side I have 1 minus cosine 2 theta over 2, and on The right side, when I square what's in the radical, that radical is going to be gone. And so I'm left with 2 times 1 minus cosine theta over 2. So my 2's are going to cancel. And I have 1 minus cosine 2 theta over 2 is equal to 1 minus cosine theta. Now I do have a double angle there on the left side, so I'm going to rewrite that to help me out here. I'm going to write it such that I apologize for the giant long pause here. I'm trying to, I feel like I should have started this, approach this a little bit differently. So I'm going to actually back up. And instead of going from both sides at the same time or going from the left side, I think I'm going to go from the right side because it seems to be slightly more complex. And so I'm going to take that half angle again, but I'm going to go from the left side to the right side, so that's still 2 sine of theta over 2 squared, and I can replace theta over 2 with a half angle. So that gives me 2 times the square root of, or plus or minus the square root of 1 minus cosine theta over 2 squared. So that's equal to sine squared theta. Well, when I square the radical, the square and the radical are gone. So I'm left with what's on top. And so now I've got sine squared theta is equal to 2 times 1 minus cosine theta over 2. And you can see that my 2's are going to cancel. And I have sine squared theta equals 1 minus cosine theta. I'm going to take that sine squared and I'm going to replace it with a Pythagorean identity. And because sine squared is 1 minus cosine squared theta. And then I'm going to subtract what's on the right and say minus 1 plus cosine theta equals 0. Well, what's going to happen is my ones are going to cancel, and I have negative cosine squared theta plus cosine theta. And I'm going to factor out a negative cosine. I'll bring some of that work over here. Way up there. So what I left off with was negative cosine squared theta plus cosine theta equals 0. And when I factor out a negative cosine, that's going to leave me with cosine theta minus 1 equals 0. And now I'm going to put some variables in there. So cosine is x, so I have negative x equals 0, and I have x minus 1 equals 0, and I'm going to solve for both of those. So on the left-hand side, that's x equals 0, and on the right-hand side, that's x equals 1. So I want to know the values for theta where x is 1 and y is 0. X is 0 at pi over 2 and 3 pi over 2. And x is 1 only at one location, and that's at 0, 2 pi. And so those are my angles right here. Apologize for that. Actually, I was solving instead of, I shouldn't have been trying to prove an identity. I was just trying to solve the equation. So you basically want to get everything over to one side at some point and set it equal to 0. Okay, that's all the notes that I have there, and you're going to do exercises from lesson 5-4.